Hi, I'm Aakash Sane. I'm a postdoc at Princeton University and GFDL, and as part of the MSCOR Alliance project, I'm working with Brandon Reichel, Alistair Adcroft, and Laura Zana. I'm going to talk about my research in parameterizing vertical mixing coefficients in the ocean surface boundary layer using neural networks. Key point of this talk is that we have employed neural networks within an existing energetic space physics framework to get the eddy diffusivity of vertical mixing. Neural networks show very high offline scale. The neural network scheme has been implemented in MOM6. This work is still in progress, and I will go into details in the subsequent slides. In a typical ocean model, the Reynolds average Navier-Stokes equations are used. The first equation shows a tracer equation for generic quantity phi. Phi can be a tracer or a velocity. The terms on the left are the inertial terms, and on the right-hand side, we see Reynolds stress and a molecular diffusion term. The turbulence problem is closed by assuming that the Reynolds stress is a function of mean flow quantities, and using the mixing length hypothesis, average of W prime phi prime is assumed to be kappa multiplied by a vertical gradient of phi plus maybe some non-local terms. The term kappa is almost always modeled as equal to a length scale L multiplied by a velocity scale V, and it might involve a non-dimensional shape function. Figure over here shows a sketch of vertical eddy diffusivity. The top blue line is the sea surface, and the second blue line is the base of the boundary layer. Eddy diffusivity is zero at the top and the bottom, and the shape function and L and V make it positive in between. In existing physics-based approaches, the shape function L and V are based on physical principles. There are many schemes which model kappa, but the different schemes disagree. Just to give you a glimpse of what I mean, here is a figure from Racklandly from 2019, and the different lines show temperature profiles from different schemes. These differences can grow and can lead to uncertainties in long-term climate projections. Not just the different schemes disagree, but different diffusivity profiles can affect global mean temperatures and mixed layer depth in a general circulation model. The existing physics-based framework we are following is the energetic planetary boundary layer framework. It has been developed by Reichel and Halberg. In the EPBL framework, the integral of turbulent buoyancy flux is constrained using a parameterization which uses high resolution data. The scheme is robust to changes in time stepping and vertical grid resolution and performs well against higher order turbulence closures and large eddy simulations. More details can be found in Rackle and Halberg's article from 2018. The EPBL scheme uses a shape function to find the characteristic length. It has an exponent gamma shown over here. I won't get into the details of the scheme right now, um, but changing the exponent from 1 to 3 has an impact on long-term simulations. The top figure shows the difference between two MOM6 runs in terms of mixed layer depth after a simulation has been run for a period of about 4 years. We can see that the mean mixed layer depth has changed from minus to plus 10 meters. The bottom figure shows sensitivity to global mean SST. Both the figures show that getting an accurate diffusivity profile is very important for accurate predictions as well as long-term projections. To get an accurate diffusivity profile which matches high resolution data as well as the true data, our approach involves using neural networks within an existing EPBL framework. We assume that kappa depends upon a shape function shown as SF, a characteristical length L, and a characteristic velocity V. The shape function depends on a sigma coordinate, where sigma is 0 is the sea surface, and sigma is -1 is the bottom of the ocean surface boundary layer. The shape function is obtained by using a neural network N1, which needs latitude, surface heat flux, surface wind stress, and the boundary layer depth as inputs. And the characteristic velocity is obtained from a second neural network N2, which requires latitude, surface heat flux, and wind stress as the inputs. We are using neural networks because they capture and approximate nonlinear relationships very well. They have excellent skill while interpolating, as in when we are within the range of the training data. And because the diffusivity is a nonlinear function of multiple inputs, neural networks should learn that relationship. And this is our hypothesis. Uh, Neural network is trained to find a relationship between an input vector X and an output vector Y. The figure over here shows a network which has two hidden layers, and that's what we are using for N1 and N2. We are using the PyTorch library in Python to train this network. Neural networks show utility and have demonstrated their strengths in physical sciences. The viewers are encouraged to check the work of Bolton and Zana, as well as Ras, Pritchard, and Gentine, among various other articles. One aspect of these machine learning methods is that they are data hungry methods. And in order to generate data, we are using high resolution GOTM simulations. GOTM stands for General Ocean Turbulence Model. And we run simulations with various forcings, such as latitude is varied from 0 to 90, surface heat flux from -400 to 400, and surface wind stress from 0 to 1. These bottom simulations are single column model. They are inexpensive to run, and a wide range of forcing scenarios can be quickly simulated. Previously, bottom simulations have been used in formulating the EPBL framework and tuning empirical coefficients. We also use the second moment capsulon closure, which is built inside GOTM. This closure uses mechanical turbulent kinetic energy conservation principles to constrain turbulent mixing. This assumes a down gradient turbulent buoyancy flux. Here is an offline comparison of the neural networks. This left figure shows the shape function from the neural network. We train on the non-dimensional shape function with respect to the sigma coordinate. This gives us the diffusivity profile independent of the vertical grid. Potentially, this network is employable in any type of vertical coordinate system, but this needs further investigation. The results over here are shown for two cases. The brown line, which shows the neural network output, shows very good agreement with the blue line, which represents the true data. The figure on the right shows network trained to predict the velocity scale V. The image below shows true velocity on x-axis and predicted velocity on the y-axis. The data is shown in blue color, and there is a black dotted line, which is the y is equal to x line. Each point is a different simulation having different forcing. The points represent all the cases simulated, such as heating, cooling, low latitude, high latitude, etc. You can see that the predicted values on the y-axis agree well with the true values on the x-axis. And this histogram shows the error between those two. So we use neural network to get the shape function, and we use a second neural network to get the characteristic velocity. And for the length, and for the characteristic length, we assume that it is the same as the boundary layer depth h. And we can see from these figures that the neural network show excellent skill when validating in offline mode. I've gone further and implemented this network in GFDL's MOM6 ocean model. This video over here shows results for two cases. Uh, One is the surface heating case, and one is the surface cooling case shown below. The green color shows the truth runs from Gotham. The blue color is the existing EPBL scheme in MOM6, and the red color is the EPBL scheme with neural network implemented inside it. The EPBL in blue and the EPBL with neural network in red show good agreement with the true data from Gotham. The diffusivity in the red color run has a shape function closer to Gotham than the blue color. This shows the strength of neural network in getting a diffusivity profile closer to the true data. We can see that the red one over here is closer to the green one also for the surface cooling case. The exact amplitude of diffusivity uh, for both the schemes is different because the neural network takes in the boundary layer depth as an input, and the boundary layer depth is calculated differently in EPBL and Gotham's epsilon. This work is under development and needs some more careful investigation to close these gaps. These are the results for diffusivity. These are the results for temperature. The temperature profile also undergoes changes at the base of the mix layer when we switch on the neural network. To conclude, a neural network framework has been developed which uses high resolution two equation closure for training and gives output of diffusivity for the boundary layer. Neural network shows excellent skill in predicting the shape function. The scheme has been implemented in GFDL's MOM6 within the existing EPBL physics framework. This guarantees constraining the energetics while providing enhancement of the diffusivity profile towards the truth data. Our method is also unique in the sense that uh, we are making sure that we are not violating any of the physics principles. Changes in the temperature profile of the single column model are also observed. Challenges and next steps. We need to quantify the uncertainty due to neural network and missing forcing factors in the network. Currently, diffusivity has been assumed to be down gradient. No non-local fluxes have been considered. The forcings are steady in time. The scheme might need some adjustments for transient cases. This warrants some more investigation. We have only trained on high resolution K epsilon runs. We need to train on the LES data. We also plan to consider Langmuir turbulence effects and a way to factor them inside the neural network. Thank you.